My name is Chalvatzaki, and I will present to you our work on revisiting grasp map representation with a focus on orientation in grasp synthesis. Grasping is still challenging for robots due to the high variability in the object's morphology. The continuous and effective estimation of the approach vector is fundamental for the successful grasp execution. State-of-the-art pixel-wise approaches fail to model ambiguities due to multiple overlapping grasping boxes with different orientations and hence cannot provide sufficient reconstructions of the grasp maps. Our problems lies in finding the optimal grasp configuration, which is the grasp center, the orientation, and the jaws opening, and also a quality measure that characterizes the success of the respective grasp configuration. The Jakarta dataset is one of the biggest grasping datasets with 54,000 images and 1.1 million annotations, which are rectangles with given center, angle, width, and height. These annotations are simulated and resulting into multiple overlapping boxes considering all possible grasp orientations and different jaw sizes, where the jaw size is a free variable that can be arbitrarily chosen during the evaluation. Morrison et al. Created ground truth maps by creating pixel-wise quality, angle, and width maps by iterating over the annotated boxes and stacking binary maps. This stacking is indifferent of the order of the boxes and finally consider only maximum jaw sizes. For the angle and width maps, the annotations are overwritten by the box that appears later in the annotations. And finally, they use binary quality maps that do not ensure a valid maximum, as all points inside the box can be considered as a possible grasping center. This means that even a hypothetical regressor cannot perfectly predict and reconstruct the annotated grasping maps, as you can see from the figure. We, on the other hand, are proposing a new representation and we partition the angle values into n bins. We do not discretize the angle values, but we instead place them inside the corresponding bins. We use soft quality maps that contain ones on the exact positions of the centers of the boxes while their values degrade at the edges of the boxes. And for multiple instances of the same grasp center, we pick on the mean jaw size. And for evaluation, we adopt the same policy with Morrison et al. To be directly comparable. This leads us to an augmented grasp map representation that contains the new angle, width, and soft quality maps, a new binary orientation map, and a pixel-wise graspness map that contains one on the positions of the maps. For the grasp synthesis problem, we propose Orange, an orientation-attentive grasp synthesis framework that is model agnostic and can be combined with any CNN-based model that is able to provide the segmentation. In this work, we combine Orange with GGCNN from Morrison et al. And UNet that are both able of performing segmentation, and we will prove that both of these networks perform better under the Orange framework. The Orange takes the augmented grasp map representation and fuses continuous and discrete information, uses the pixel-wise graspness as a regularization and the bin-wise orientation attention in order to force the focus of the network on the local maxima of graspness. From our ablation study, you can see that the full proposed model with pixel-wise graspness and bin-wise orientation attention achieves the best results in the IOU threshold of 0.25 and 0.30. While we can see that using binary maps over the soft quality maps produces 4% less accurate grasp predictions, while training the unit under in the way suggested by Morrison et al. Succeeds only 89.85%. Compared to the other works on the Jakarta dataset, we can see that we gain the state-of-the-art performance under the Orange implementation. And we can say that the innate morphological characteristics of objects may hinder the learning of robotic grasping, and structures like cyclical objects offer a wide range of plausible grasping orientations. We optimally would like to acquire a mapping of graspness of all possible configurations and then sample from the most likely configuration for achieving different manipulation tasks. And we revisited the grasp map representation by classifying the grasp into discrete orientation beans and regressed their values for a continuous estimation per bean. This orientation map acts as a bean-wise attention mechanism over a soft quality map, and we proposed ORAND that can be combined with any approach capable of performing segmentation, boosting its performance and generating accurate grasp predictions. Thank